All right, so let's go on to the next quantum number. It's called angular momentum quantum number. It is a lowercase l. I always try to draw it as a script L with a loop so that it doesn't look like a number 1 or a capital I or something like that. I learned that lesson the hard way on writing an exam when I was using a sans serif font, and I had lowercase l and 1 and I and all these various things that were looking exactly like. So use a script lowercase l, okay, for the second quantum number that we're talking about. So the angular momentum quantum number, you should know that name too, because sometimes it's called that. Okay? That determines the shape of the orbital. Okay? So possible values of L. L are also integers, but unlike n started at 1. Okay? L starts at 0. Just make a little note of that here on that last page here. N starts with 1. L starts with 0. Okay? And in a second here, we'll talk about what this maximum number is. But for right now, let's just talk about L, 0, 1, 2, and 3, because those are really the only values that, that have any practical usage to us. Okay? So I already showed you this model here. This is a spherical orbital. L is 0, but a lot of times we use the letter S for that, and there's a big long history to that with spectroscopy and naming the certain kind of lines that come off from light and so on. So it's handy though because S is spherical in shape. That's not really where that S came from, but that's an easy way to remember it. Okay? So we have spherical orbitals. P orbitals have 2 lobes like that. So what that means is that an electron could be spending some time inside of here or inside of here, okay? But not really spending much time right where the nucleus is. Okay? Different from an s orbital, where the actual concentration of where that electron spends most of its time ends up being fairly close to the nucleus, okay, on the inside. Okay? Here, there ends up being a node, and a node is just an area where there's no electron density. Okay, where the electron spends none of its time. And the shape of this actually comes from the wave-like properties of an electron. If you imagine an electron inside of here that is acting like a wave, it could be sort of like a jump rope, okay, where it goes kind of up and then down and up and down. You can sort of think of it like that. But then, if you have a jump rope and you start doing it a little faster, you can get it where half of it is kind of going up and half of it is going down, like that. That's sort of where this shape comes from. If you can imagine sort of going up like that and then down like that, or going kind of up like that and down like that. But either way, it's sort of staying still at the middle, which means it's not really spending much time there in the middle. Okay? So that's what a p orbital looks like. It has 1 node. Sometimes we draw a dotted line like that. That's 1 node. Okay. A node is and 3-dimensionally, a node is actually a plane. Okay. So if I put a piece of paper or my hand or something down the middle of that, that would be the 1 node. Okay. L equals 2. Those are called d orbitals. They are, for the most part, clover-shaped. I'm going to show you a picture with some more of them. But they have 2 nodes. The f orbitals become far more complex in shape. That's just one of them. That's that. But some of them end up looking kind of funky too. But again, as L increases, the number of nodes sort of increases with that. If we sort of imagined a node here on the xy plane, okay, a node there on the xz plane, and a node on the yz plane. Okay? If we had those 3 nodes, that would sort of define that shape. Okay? So, in general, it's higher energy as L increases. Okay? So, the lowest energy of these orbitals overall is S. Okay? As we increase the number of nodes, which increases the sort of places that those electrons can be, becomes higher in energy and more complex. Okay? So when we take N and L together, they define what is called a subshell. Okay? And as we'll see in a little bit, a subshell is sort of a general area where electrons can be sort of categorized in a molecule. Okay? So when N equals 1, L equals 0, and that's the only option because the maximum value of L is N minus 1. Okay? So for whatever our N value is, okay, L could be any value starting at 0, okay, maxing out at N minus 1. So if N is already 1, L equals 0, that is N minus 1, so there are no other possible values of L. Okay? That just means that if our principal quantum number is 1, okay, we have a spherical orbital, and that's it. Okay? Subshells are usually labeled with the N as well as the letter then that subshell represents. Okay? So a 1s subshell would be a spherical orbital with electrons that are in the first principal quantum number. Okay? But any electron that's n equals 1 can only be in a spherical orbital like this. Okay? If we have an electron in the second principal quantum number, we could have L equals 0, which is a 2s. Okay? And the only difference between 1s and 2s, if you draw 1s as a sphere sort of like that, 2s is also going to be a sphere, but it's going to be larger. Okay? Because remember, n sort of defines the size, okay, and energy most of all. L defines the shape. So 1s is a small sphere. You could think of that with hydrogen. Okay? When we just draw sort of those levels like that, the ground state could be 1s that's like this, but an excited electron could be 2s, which would be that same electron but now filling a larger area. Okay? So flying around in a bigger space. And then when it gives off its energy, it kind of shrinks back down to being within that smaller area. Okay? So the difference here in n equals 2 is that now we could also have L equals 1. That's 2p. Okay? 2p, and we'll talk in a second about how many there are, but okay, those are dual lobed, okay, so different shape. Okay? See if you guys can see the pattern. N equals 3, L equals 0. What would we call that? 3s, yep, L equals 0 is an S. Okay? And 3s would be spherical again, but larger yet. Okay? N equals 3, L equals 1, we would call that 3p. Okay? It would be two-lobed again, but larger than 2p. Okay? But now we could do 3 and 2. Look at your table up above. What would we call that? 3. Yep. SPD. Okay? That's 3D. Okay? So, N still sort of refers to what are called shells. Okay? That's why these letters are called subshells, because they're kind of divisions within the shell. Okay? So, third shell Okay. Let's do 4. We can go 0, 1, 2, or 3, right? So that would be 4, 0 would be 4 S. 4, 1 would be for P. 4, 2 would be for D. 4, 3 would be for F. Okay? So the first time an F-type orbital is used is not until we're already into the 4th shell. Okay? So L, 0, 1, 2, or 3, S, P, D, and F. Okay? You should be able to say that to yourself in your head. I think that's a... let's put a star by that. Okay? Let's make that extra important. 0, 1, 2, and 3, S, P, D, and F. You're going to need to be able to say that. Okay? And like I said, those names largely, those letters largely are historic from before they even knew what these orbitals looked like, what their shapes really were. The other thing I want to warn you about is that these orbitals are not actual things. Okay? They're not actual little spheres and little things inside of an atom. It's just defining an area that an electron spends most of its time. So if we had a d orbital, it would just look like an electron sort of zooming around, but if you looked at that over time, you would see that that electron is spending almost all of its time within the confines of those particular orbital areas. Okay? That's all we're talking about here. Okay. So, principal quantum number was n, and what does n really mean? What does n influence the most? Energy and what else? What's the difference between 1s and 2s? Size. Okay? So n is mostly size when it comes to the orbitals. It's also the most important indicator of energy. Okay? I think we said that right here, right? Size and energy. Okay? L determines the shape. Okay? We probably better write here that they also have minor energy differences as well. Okay. I think we showed that it goes S, then P, then D, then F in increasing energy because we're adding those nodes each time. Okay.